Okay, so we're gonna pick up where we left off last time. So we were looking at, we just started the calculations, right? And so we discussed what Faraday's constant is. We spoke about the electric charge and how we calculate electric charge. So I introduced you guys to this formula, which is basically Q is equal to I times T. So that's kind of like the governing equation for all things electrochemistry at the CXC level, at least, where you're given the current that flows through the electrolytic cell and for what the length of time that it flows. And from that, you can calculate the charge that's associated with that electrolytic cell, right? Because the charge is dictated by the amount of current and the length of time that you flow that current for, right? We spoke about Faraday's constant, which is, I said, is a number that you guys should commit to memory. And Faraday's constant is essentially the quantity of electric charge that's carried by 1 mole or 1 mole of electrons or 1 mole of singly charged ions, right? And its approximate value we said is 96,500, and the unit is coulombs per mole, right? So we're all good on that, right? So here we have the statement of Faraday's constant again. And we have Faraday's first law here as well, which states that the mass liberated, so the mass of whatever your substance is or your compound is, that gets liberated either at the anode or the cathode during electrolysis is directly proportional to the amount of electricity which is passed through the cell. So the more electricity you pass through the cell, the more mass of stuff you'll get. So if you want a lot of stuff deposited at your anode or cathode, you have to flow a lot of electricity and for a long time, right? If you want a large mass, right? So that's essentially what Faraday's first law says. And the second law, I modified this statement for you guys from last time. So essentially the second law speaks to this idea of Faraday's, and I'm gonna pop that up here on a whiteboard because I think we need to have this written out. Let me share that. So let me stop sharing this and then share the whiteboard. So essentially I'm gonna break down the second law, Faraday's second law for you. And then this will be your jumping off point for today. So this is Faraday's second law, right? And this is kind of what I wanted to really home in on today and clarify for you guys. So the second law is talking about this idea of Faraday's, right? And it says that the number of Faraday's required to discharge 1 mole of an ion at an electrode is equal to the size of the charge on the ion. So guys, this is very important. I want you to remember this. And I'm going to read it again and emphasize the key points from here, right? Because this is very, very important going forward. Very, very important. So the number of Faraday's required to discharge 1 mole of an ion, right? So pay attention to the quantities that they're talking about there now. The number of Faraday's, so it could be 1, 2, 3, 4, 5, 6. The number of Faraday's required to discharge 1 mole of an ion at an electrode is equal to the size of the charge on the ion. Okay, so if we have species that have a single charge on it, so like that sodium ion that we spoke about before, sodium is the size of the charge is +1. So let me just write that. So the size of the charge is +1. Has a charge of +1, right? So 1 Faraday will be required right, to discharge 1 mole of sodium ions, right? Everybody got that so far? Guys, engage with me, now talk to me and let me know, right? So magnesium we know is very popular for being in group 2. It has 2 valence electrons, so it has a charge. The size of the charge on that magnesium ion is +2. So magnesium has a charge of +2. So how many Faradays would be required to discharge 1 mole of magnesium ion? Somebody tell me, just unmute and tell me. We're not using the chat today because I can't check the chat and do all these things at the same time. So just unmute yourself and engage with me. If magnesium has the size of the charge on a magnesium ion is +2, right? How many Faradays would be required to discharge a mole of that per our Faraday's second law that we just wrote up there? Anyone?
It's 2 Faradays.
Exactly. Exactly. That's exactly right. So I love that we're all on the same page with that. Will be required, right? To discharge 1 mole. Guys, pay attention to that, you know. It's to discharge 1 mole of magnesium ions, right? All right, so then the third, for the case where we have a size of the charge being 3, that would be aluminum. Aluminum is in group 3. It has 3 valent electrons. It's 3 electrons that we would need to move around, right? So aluminum has a charge of +3. So how many Faradays now?
3.
Okay. 3. So 3 Faradays will be required to discharge 1 mole of aluminum ions. So I think we're all on the same page now. Aluminum. So we're on the same page now. So this is Faraday's second law. Let me bring this up. Faraday's second law. We spoke about the first law before, and can somebody tell me what the first law is, and then we'll move on. So the second law is here, and I think this is clear in all of our minds now, right? So let's go back to the first law. What's the first law again? And then we'll move forward. What's the first law, somebody? Anybody, just tell me. Anybody just tell me. What is the first? What is Faraday's first law again?
Electric charge relates directly proportional to the amount of current being supplied.
So repeat that again for me, Jamar. Say it again.
I said electric charge relates directly proportional to the amount of current being supplied.
That's exactly right. And then by extension, what does that influence? What about your final product does that influence? So your electric charge is proportional to your current that you flow. That's exactly right. And then by extension, the quantity of charge then feeds into the mass of the product that you get, right? At either electrode, so either the cathode or the anode, the quantity of electric charge is proportional to the current, but and by extension, the quantity of electric charge dictates what mass of stuff you're gonna get deposited at either the anode or the cathode. Okay?
Yes, ma'am.
Okay, so I'm gonna clear this now. Is that okay? Do you guys have this already? I'm gonna clear it, okay?
Miss, give me 1 minute.
Okay. So then we're going to jump into some problems now, and we're going to start with the problem that we did last class. Let's just kind of show you that again, and then we move on.
Finish, miss.
Okay, all right. So I'm going to clear it now, clear all my drawings. I'm going to stop sharing that and go back to my presentation to this question that we did last time, right? And so essentially, this is a question that you're applying Faraday's first law. So it shouldn't be anything fancy where we need to like rely on the second law too much, because it's just asking us about the mass, and it's sodium chloride, which are singly charged species, right? So, all right, so let me grab my pencil here. So sodium chloride is our electrolyte, right? So that's our electrolyte. We're electrolyzing molten sodium chloride. So that has the ions of interest are Na plus and Cl minus. We're flowing 5 amperes of current. So that's I, right? So I is equal to 5 amperes. And then the time, we said we need time to be in seconds. We're using the SI units, right? So what's this again, guys? In seconds, 32 minutes and 10 seconds. I think that was 1930 seconds, right? 1,930 seconds, right?
Yes, miss.
All right, so then from our first law, and of course, Faraday's constant, I said commit that to your memory. Faraday's constant is 96,500 coulombs per moles, right? Now, this is a first law problem. And from the first law, we know that Q is equal to I times T. That's exactly what Jamar just said. Q is equal to, so the quantity of the electric charge is proportional to the current that's flown, right, through your electrolytic cell. And so let me write that. Let me write out that equation. So that's your step 1, essentially. More often than not, I would say that you can follow that pattern, right? So start with your step 1 being you're calculating the quantity of charge that's being flown, that's being flown through that cell, that electrolytic cell. So calculate that first so you know what you're working with, right? So calculate your Q first. Down. Let me bring it down. I don't need an arrow. Okay, let's try this again. Let's try this. All right, see, don't know. All right. So Q, right? Q is equal to I times T. So can somebody calculate that Q again for me real quick? Put that in the calculator and tell me what that Q is. So that's 5 times 1930. What's that Q? And tell me the units as well.
9,650 C.
9,650 coulombs.
Yes,
So
miss.
that's the charge that we're working with, right?
Yes, miss.
All right, so that's your step 1. Step 1, you find the amount of charge that you're working with. Step 2, you write your half equation, right? That's associated with the species or the product that they're asking you about. So in this case, they're asking you about the chlorine, right? And that chlorine is a neutral species, and that's coming from your chloride ion. So now we know that the chloride ion is an anion, and where do anions migrate towards? Where do they go? Which electrode?
The anode.
Okay, so essentially then, what we're writing is the half equation for the anode, right? So we say at anode, let's do that. At anode, let's do this. Let's write out exactly what happens. At the anode, the chloride ions get, what do they get? They get oxidized or reduced. What happens to them?
Oxidized.
They get oxidized. So let's write that. They get oxidized, right? So now what does that mean? They get oxidized mean that they lose their electrons, right? They lose electrons. So Cl, let me just write it without it being balanced first. Cl minus, right? Oh, it's losing electrons. So you can say minus E, negatively charged. It goes, then it forms a neutral form, which is the chlorine, diatomic chlorine gas that has a zero charge there. So it's going from -1 to 0, right? So there's an increase in the oxidation number from -1 to 0. So that increasing oxidation number tells us that it got oxidized, right? So we're all good there, but our molecules, our atoms aren't balanced, and our charge is also not balanced, right? So let's balance the number of molecules. So then we'll get 2 here. So we have 2Cl minus ions. And because we have 2Cl minus ions, then the two of them combined together, they're gonna need to lose 2 electrons, right? You see that? So to then get to that neutral chlorine molecule. Are we all on the same page as far as half equation goes? Are we all good on this?
Yes, miss.
Okay. So essentially, we know that, so based on this balance equation then, right? I'm gonna write it on here. 2 moles, when 2 moles of chloride ion get discharged, we form 1 mole of chlorine molecule, right? When 2 moles of chloride ions get discharged, we form a mole of chlorine molecule, right? No, but what that also means is that if 1 mole of chlorine ions get discharged, then we're gonna get half a mole of chlorine molecule, right? You see that? This is just like stoichiometry stuff, mole concept stuff, right? Do you guys see that?
Yes, miss. Yes,
So
miss.
when 1 mole of chlorine ions get discharged, we're gonna get half a mole of chlorine molecule, right? So what this means is what that means is if we use what we know from the second law, 1 Faraday, I'm gonna write it up top. I'm gonna write it up here. 1 Faraday is required to discharge 1 mole of that Cl minus ions, right? So 1 Faraday is required to discharge 1 mole of chloride ions, and that's because the charge on it is -1. The magnitude, the size of the ion is the size of the charge on the ion is -1, right? So we're good on that. We need 1 Faraday to complete this transfer of that 1 mole of chloride ions, and that 1 mole of chloride ions is gonna get us half a mole of chlorine molecule, right? Are we all good there? Half a mole of chlorine molecule, okay? Are we good on that?
Yes, miss.
Okay, so then now, let me erase this stuff. So I'm erasing this stuff to get some space. But can anybody else tell me what's next? Like what follows next? What follows that progression of what we're doing? Can anybody tell me what follows next while I make some space to complete this?
Let me find the molar mass of chlorine.
Yeah, so what's that? Tell me what that is.
It's 35.5 for 1 mole and 71 for 2 moles.
So it's 35.5 is the molar mass or the relative atomic mass, and a molecule of chlorine is made up of 2 atoms, right? So it's 2 times 35.5, right? So that would give you 71 grams, right?
Yes, miss.
Okay, so where we are, so in terms of Faraday's now, so just to go back up here for a little bit, that top line that I just wrote, I said 1 Faraday, right, is gonna discharge 1 mole of chloride ions, and the reason why is because the size of the charge on the chloride ion is 1 minus 1, right? And from the stoichiometric equation, we know that when we discharge 1 mole of chloride ions, we're gonna get half a mole of chlorine molecule, right? So are we all on that same page now?
Yes, miss.
Okay, so then now we have to find out how many Faradays we actually have, because that 1 Faraday is a hypothetical situation. It's like, okay, as the equation is written, 1 Faraday is going to be needed to discharge 1 mole of chloride ions, which will give us 0.5 moles of chlorine molecule. But we don't have 1 Faraday. Oftentimes we don't have the basis as to what they're giving us. We have exactly what the question tells us that we have. And the question told us, based on our calculations, that we had 9,650 coulomb. That's how many charges flowing through the system, right? So that's how much charge we have. And that's what dictates the mass of chlorine that will be produced, right? So what we have to do then is find how many Faradays that quantity of charge translates to. And to find that, what do we do? Can anybody remind me what we do? So we have our quantity of charge being 9,650, and we want to put that in a form of Faraday. So how do we convert that to Faradays? So we know how many Faradays we actually have in the system, right? Can anybody tell me how you do that calculation? Any? Okay, guys. So sorry about that. I had to step out for a little bit there. So where are we now? Who did that conversion for us? Who did that conversion for us from the charge to Faraday? So we have 9,650 coulombs. How do we put that in a Faraday form now? How many Faradays is that? Anyone?
Yeah, 0.1.
So it's 0.1. How did you get that, Jamar?
I divided it by the constant. Faraday's constant.
Divided by Faraday's constant. It's exactly right. So let me write that real quick. Maybe I should just use a text box. It's just easier. All right, so that's number of Faradays is equal to 9650 divided by Faraday's constant, which is that, and that gives us 0.1 Faradays, right? And so from right above that, you see that 1 Faradays get us 0.5 mole of Cl2, which is the same as 0.5 times 71 grams, which is, how much is that, guys? That's what 1 Faraday gets us. What's that? What's that? 0.5 times 71 is what?
$35.5.
Okay, so 35.5 grams is what we get for 1 Faraday, right? For 1 Faraday, we get 35.5 grams. How much do we get for 0.1 Faradays? Anybody can do that math real quick? It's just a ratio thing that we're doing now. It's a ratios now. We're working with ratios now. If 1 Faraday gets us 35.5, how much is 0.1 gonna get us?
Miss 7.1, miss.
How much?
Miss 7.1.
How did you get 7.1?
Miss
Because like, go ahead.
Miss 0.1 times the 71, miss.
Well, you would multiply by the 71 now, because remember that now what we said is that 1 Faraday actually gets us 35.5 grams, right? Because the 1 Faraday gets us half a mole, which is 35.5, right? So we've moved on from 71 now, if that makes sense.
Miss, I got 3.55.
So it's 3.55, and the reason why it's 3.55, Jamar, is because if you look at it in terms of ratio, right? 1 Faraday gets us 35.5 grams. 0.1 Faraday is just moving that decimal point 1 unit back, 1 place back. So that's just that will just get us 3.55. You see that, Jamar? We've moved on from the 71 now, because we don't.
Oh, miss, it's because I did it another way.
Oh, what was the way that you did it?
Miss, after I wrote the half equations, miss, I said 2 chloride electrons yield 0.1 moles of chlorine. And then I found for 1, which is 0.05 moles of chlorine. And I times that by the 71, miss, and I got 3.55.
Okay, so that's your final answer. We ended up at the same place, right?
Yes, miss.
Okay. Okay, so there, as long as you're clear on the methodology that you use and it makes sense and it's consistent, then it's fine if you use a different route to get to where we got to get the same answer, right? So are we all clear on this? Because we're gonna move on now to another calculation. So are we all good on this?
Yes, miss.
Okay, so I'm gonna clear that now and then move on to the other one. Which is this. So this is like directly applying Faraday's second law, which is the Faraday's stuff, right? So during the electrolysis of copper sulfate solution, if 0.5 Faraday is used, what mass of copper will be deposited at the cathode? So in this particular case, whereas for the previous example, we had to calculate the Faradays from the Q that they gave us, right? That's what we did just now. But in this particular case, they're already telling us that 0.5 Faraday is used, right? So we have to somehow correlate that amount of Faraday to the mass of copper that will be deposited at the electrode, right? So do you guys see what they're asking us here? So the first step, so tell me what my first step would be in this particular case. What's my first step here? because I don't have to calculate Q anymore. I know what Q is in terms of Faraday. So what's gonna be my first step?
Miss, writing a half equation.
Exactly, and that's for at the cathode, right? Because they're asking us about the cathode, and at the cathode, reduction takes place, right? At the cathode, reduction takes place. So what are our ionic species in this particular case? What are our species of interest that are in copper sulfate? What are our ions here? We have Cu2 plus, that's our cation, and our anion is SO4 2 minus, right? So this is our cation. So at the cathode, cations go here. Cations go here, and they get reduced, right? In that process. So cations go there. So the cation in this particular example is Cu2 plus. Now Cu2 plus is gonna get reduced. So that means that it's gonna gain electrons, right? Its reduction is gain, it's gonna gain electrons. So then it's gonna be Cu2 plus, Cu2 plus, right? That's plus, sorry about that. Let me undo that and make it clearer. If I can get more pencil now. So Cu2 plus is gonna gain 2 electrons because that's what you need to balance out that 2 plus, right? So Cu2 plus is gonna gain 2 electrons, and in gaining those 2 electrons, it's gonna become neutral. It's gonna just become copper, solid copper, right? It's gonna become solid copper. It was aqueous, so aqueous over here. It's gonna become solid copper now. So that's your half equation, right? So from this half equation, or okay, let's think about the Faraday's second law, right? We have Cu2 plus. So what's the size of the charge on that ion? What's the size of the charge on that Cu2 plus ion? What's the size of that charge?
0.5.
The size of the charge. So like, what's the magnitude of the charge that's associated with copper? It's 2 plus, right? It's 2, right? Because it's Cu2 plus, so that's the size of the charge on that ion is 2 plus. So then to discharge that, how many Faradays would we need? To discharge 1 mole of that ion, how many Faradays would we need?
2.
Given that the size is 2. How many? How many Faradays?
Miss 2?
Okay, so we need 2 Faradays to discharge 1 mole, right, of Cu2 plus ions. And from that 1 mole, we get 1 mole of solid copper. Do you guys follow that from the stoichiometric equation? So we're gonna need 2 Faradays because the size of the charge on copper is 2. And so that 2 Faradays is needed to discharge 1 mole of those copper ions. And from discharging that 1 mole of copper ions, we're gonna get 1 mole of solid copper. Do you guys follow that?
Yes, miss.
Okay, so then now, okay, and how much is 1 mole of copper? How much does 1 mole of copper weigh? What's the relative atomic mass of copper? Let's just complete this here. Let's just
64.
How much is it?
64.
Okay, so let's do that. So let's just add that line here, right? So that's the same as saying we have 64 grams of copper, right? So let me say it again. 2 Faradays is required because the size of the charge on the ion is 2, on the copper ion is 2. So we need 2 Faradays to discharge a mole of those copper ions. And based on the balanced half equation, a mole of that Cu2 plus ion is going to give us a mole of copper solid, right, at the cathode, which is the same as 64 grams of copper. So are we all on the same page there?
Yes, miss.
Okay, so then can somebody tell me what's next? Because we're home free now, we know. We're home now. We know that 2 Faradays, essentially, we can distill all of this to say that we know that 2 Faradays, essentially, right, is going to get us 64 grams of copper, right? So how much is 0.5 Faraday going to get us? We know what 2 gives us. So what's 0.5 going to get us? 0.5, because that's all we have. So what's the 0.5 going to give us? How many grams of copper? So X is equal to what? What's the answer here, guys? 2 Faraday gets us 64 grams, but we only have half. We only have 0.5 Faraday. That's what they told us. So essentially we have 4 times less than the amount that would get us 64. So essentially we're dividing the 64 by 4, right? And what's that?
If you divide 64 by 4, you would get 16.
Exactly. So it's just a ratio thing. Do you guys get that?
Get in there.
Yes, miss.
Okay. So let me just recap everything. I just want to recap this because this is crucial. This is like very important, right? So they're asking us that with this, we're electrolyzing copper sulfate, copper 2 sulfate. So pay attention to what's in the parentheses. We're electrolyzing copper 2 sulfate, right? And because it's 2 sulfate, it tells you immediately that you're gonna need 2 Faradays if you're focused on the cathode, because that's the charge on the copper ion. The charge on the copper ion is 2. So you're gonna need 2 Faradays to discharge a mole of that. So let's just like throw that out there for now and park it over there. It already is hinting that we're gonna need 2 Faradays because the charge on the copper is 2, right? But okay, so they're telling us that, oh, we're using 0.5 Faradays. What mass of copper will be deposited at the cathode? So right now you're clued into that you need to focus on the cathode. The cathode is where the cations are gonna go. Cations are positively charged. And in this particular case, in this electrolytic cell, the positively charged species is the copper 2, is the Cu2 plus, right? So we write our half equation that corresponds to that Cu2 plus being reduced because it's reduction that takes place at the cathode. So that's exactly what we wrote there. When we wrote Cu2 plus is gonna gain, because reduction is gain, Cu2 plus is gonna gain 2 electrons. And by gaining those 2 electrons, you end up with neutral copper, just your copper metal in solid form. So that's what that half equation that we wrote just told us, right? So are we good up to there now? This is just a recap, right? We wrote our half equation. Cu2 plus is going to gain 2 electrons because it's at the cathode and it's reduction, and reduction is gain. And when it gains those 2 electrons, it's going to now become copper solid, neutral, right? So reduction takes place. You're going from a 2 plus charge to a 0 charge now, because copper solid by itself doesn't have any charge on it. So it's just 0 now, right? So you see you're going from +2 to 0. That's a reduction in your oxidation number. So again, we know reduction is taking place, right? Do you all follow that?
Yes, miss.
Okay. All right. So now, as we mentioned, we're talking about copper 2 sulfate, which tells us that the charge on the copper ion is 2, right? And we know based on Faraday's second law that if the charge on the ion is 2, then we're gonna need 2 Faradays to discharge a mole of that ion. So that's exactly our next step there. We said 2 Faradays is gonna be needed to discharge a mole of Cu2 plus. And based on our balanced half equation, when we discharge that mole of Cu2 plus, we're gonna get a mole of copper, right? Are we good so far?
Yes,
Yes, sir.
When we discharge that mole of copper, that's the same that when we get that 1 mole of solid copper, that 1 mole of solid copper is the same as 64 grams of copper, because a mole of copper weighs 64 grams. That's the molar mass of copper, right? So that's how we made that transition from now moles to mass, okay? So now we're on the same page now. 2 Faradays is gonna get us a mole of copper, which is 64 grams. That's what 2 Faradays does, right? And that's what we get from our half equation. 2 Faradays gets us 64 grams of copper. Now, the question tells us that we only have 0.5 Faraday. We don't have 2. 2 is like a theoretical number. We don't have 2, but we know what 2 would get us. We know that 2 would get us 64 grams, but we don't have 2. We only have 0.5 Faraday. And 0.5 Faraday is essentially 4 times less. It's 2 divided by 4, right? So that 2 divided by 4 is that 0.5 Faraday that we end up with. So that means that that 64, we have to divide by 4 as well, because it's a ratio now. So we divide that 64 by 4, boom, 16 grams of copper is what we're gonna then get. Do you guys see that?
Yes, miss.
Is that crystal clear to you guys? I want it to be crystal clear. Is it crystal clear?
Yes, I can do a quick run through again, please.
Okay, which part of it is like tripping you up?
Well, no, it's because I just joined the class.
Okay. So let's see. Let me see. So this is a question that's focusing largely on Faraday's second law, right? So Faraday's second law tells us that the amount of Faradays that's required to discharge a mole of ions is the same as the amount is the same as the size of the charge on that ion, right? And if we look at this question, we see that we're electrolyzing copper 2 sulfate. So immediately we know that the size on the copper sulfate, the size on the copper ion, the charge is 2. So we're gonna need theoretically 2 Faradays to discharge a mole of that copper ions, and then let's just leave it at that for now. But we know that essentially from Faraday's law, we're gonna need 2 Faradays to discharge a mole of Cu2 plus ions. Is that clear so far?
Yes, miss.
Okay. So then the next step is, okay, they're telling us that we have 0.5 Faraday, that's good. We don't have 2. 2 is theoretical, we don't have 2, we have 0.5. Just keep that in your mind right now. Or if you were marking up on this, you just underline that, okay, we have 0.5 Faraday. Keep that in mind. 0.5 Faraday is what we have, we don't have 2. So they're saying what mass of copper would be deposited at the cathode. So now our first step is to write our half equation for what takes place at the cathode, right? And at the cathode, we know that reduction takes place. At the cathode, reduction takes place. So whatever your species, your ion is of interest, which is then your cation, of course, because we're at the cathode, and cations are what go here. Cations go here. Cations go towards the cathode, right? So that's your Cu2 plus in this case. So we are then supposed to write a half equation that shows the reduction of Cu2 plus. So that's exactly what I did here. Cu2 plus 2 electrons, right? It's gonna, reduction is gain. So it's gonna gain 2 electrons. We have a charge of plus 2. So we're gonna need to gain 2 electrons to then become neutral copper, this copper solid, right? So that's what this half equation here tells us, that at the cathode, the Cu2 plus ion is gonna gain 2 electrons and become copper solid. That's reduction, because the Cu2 plus is now becoming Cu0, because the copper by itself doesn't have a charge on it, it's just 0, right? So you're going from +2 to 0. That's a reduction of your oxidation number. So you can see that that checks out. This is in fact reduction. So we know that our half equation is correct. Are we good up to that point?
Yes, miss.
Okay. So then now, as I mentioned earlier, we're gonna need 2 Faradays to move that 1 mole, to discharge 1 mole of Cu2 plus ions. And the reason why we're gonna need 2 is because the charge on the copper is 2 plus. So because the charge is 2 plus, we're gonna need 2 Faradays to move to discharge that 1 mole of that, right? That's what the second law, Faraday's second law, tells us. It says that the amount of Faradays that we need is the same as the amount of charge, the size of the charge that's on the ion. So because the size of the charge is 2, we're gonna need 2 Faradays to discharge a mole of that ion, right? So that's what the second law tells us. And from here, we can see that if we are able to discharge a mole of Cu2 plus ions, we're gonna then get a mole of copper solid, right? So now we're getting closer and closer to our answer. The question is asking us what mass of copper solid will be deposited at the cathode. So we know that if we can use our 2 Faradays to discharge our 1 mole of Cu2 plus ions, we're gonna get a mole of copper solid. And that mole of copper solid actually weighs 64 grams because that's the molar mass of copper. So we're getting closer and closer to our answer now. So essentially, when we distill this down, we say that now 2 Faradays is essentially just gonna get us 64 grams of copper. 2 Faradays gets us 64 grams of copper. But we don't have 2 Faradays. We only have 0.5 Faraday. That's what the question told us. And so because we only have 0.5, we have to find how much mass are we gonna get from 0.5. So if 2 gives us 64, then 0.5, which is a quarter of 2, is gonna get us a quarter the amount of mass that the 2 gave us. So the quarter of 64 is then 16. So does this make sense now?
Yes, miss.
It's clear?
It's yes, miss, it's kind of clear.
If there's any question, let me know, If there's anything that's still lingering, let me know. Right? Okay, so I'm gonna clear this now, okay? Is that okay?
So for the half equation, you use the mole ratio for say 2 Cu2 plus and 1 electron and 1 copper solid.
Wait, can you speak a little bit louder? I can't really hear you. I don't know why.
It's from the mole ratio. You get those numbers from the coefficient.
Yeah, so essentially from the coefficient we get the coefficient part that we got, we say 1 mole of Cu2 plus would get us 1 mole of copper. So that's what this number, that's where this comes from. That's from the mole ratio, from the half equation. And then the 2 Faradays comes from Faraday's second law, which tells us that because the charge on the copper is 2, we're gonna need 2 Faradays to discharge a mole of this, right?
Right.
So you're good now? Is that clear now?
Yes, miss.
Okay, so we're gonna move on to another question now. Okay, so this one now is increasing the complexity, but it's nothing that you're not familiar with because we did spend a lot of time doing more concept. So you know, you're gonna know how to do this, right? So I'm gonna set it up for you guys, but I want one of you to do it, right? Or collaborate on doing it, right? So dilute sulfuric acid. So let me just write that down what that is, right? So that's H2SO4, and it's in its aqueous state, right? Is electrolyzed using platinum electrodes. So what kind of electrodes are these? What class? Platinum.
Inert.
It's inert, right? So you know we don't have to worry about any potential ions coming from here. So that's good. So this is good for us. This is good news, right? Now we're electrolyzing dilute sulfuric acid. So what I want us to do here is that this is our electrolyte. It's dilute sulfuric acid, it's aqueous. So let's spend some time right now to identify what our ions actually are. Because the next step would be to, of course, calculate. All right, let me do that. Let me just do it in this particular case. Let's kind of like standardize the procedure that we're gonna use. So let's say step one, identify your ions, right? Identify your ions. So break these up into your cations and your anions. So let that be your step one. Let that be your step one at all times. Identify what your ions are, the cations and the anions, right? Step two, determine which ion, right, is gonna get discharged at each electrode, right? Where's my thing? So that's your step two. Determine which ion is gonna get discharged, especially when it's like complicated like this, where it's like an aqueous solution and you know that there are a bunch of different ions in it that could potentially, you know, that they're competing, which we spoke about in our first session, well, maybe our second session, when we were talking about the electrochemical series, right? So that's why I said, okay, start off by identifying your ions, the cations and the anions. Then you're gonna determine, oh no. You're gonna determine which ions are gonna get discharged at each electrode. So are we good up to that point?
Repeat this.
Are we good up to that point? Step two. Step three now. Are we good up to that? Are we good at the steps so far that we have to take?
Yes, miss.
Yes, miss.
So then what's step three? What would you think is step three?
Half equation.
Step three is already the half equation.
We would have find
Oh,
correct first, miss.
So okay, so let's see. Let's write the half equation third, right? So write, God, I don't know why this is such a struggle right now. Anyways, let me just write in a different text box. All right, so write your half equations. Write the half equation. Since we're like focusing on our electrodes now, write the half equation. That's your third step, right? Right. Write your half equations. And then after you write your half equations now, calculate Q is equal to IT, right? Calculate Q is equal to I times T. And then we can pick up from there. How about that? How does this sound? Then we can pick up from here. figure out what the next step is going to be. So who can identify the ions that are in this for me? This is a very this is not as straightforward to write a half equation. There are things that you have to know about what's happening here, right? You have an aqueous solution of sulfuric acid. So it's not just sulfuric acid. There's water. There are water molecules present here as well, right? And so there are ions. What happens when water gets ionized? What are the species that come from that?
OH, hydroxide, and
oh, you're very low. I can't hear a thing that you're saying. You're very low.
Miss OH minus and OH and hydrogen.
Okay, so I think I hear you clearly. So you're saying that from the water, you would get OH. You would get OH minus and H plus, right? And from the sulfuric acid, what would you get? H.
And I get sulfur and oxygen.
Yeah, so SO4. 2 minus. And then what else?
Oxygen.
Oxygen is when you actually write out the equation, right? But we're just writing the ions now, so we're identifying our ions. No, but okay. You are right, is that when you actually oxidize the hydroxide, you're going to get oxygen in the end, right? But for step 1, we're identifying our ions. So from H to SO4, we have H plus and SO4 2 minus. And then from water, we have OH and H plus. So we know that our cation then is H plus, and our anions, this is where it gets tricky, because now we have to choose between OH minus and SO4 2 minus. Which of those two are gonna get preferentially discharged at where are those gonna go? Those are our anions. Where are those gonna go?
Anode, miss.
The anode, right? So out of those two, which one of them are gonna get preferentially discharged at the anode, and why? That's my question for you before we progress any further. So our cations are it's just H plus, really. H plus, and then the anions that move towards the anode that get oxidized at the anode, right? It's SO4 2 minus and OH minus. We have to choose which one, because it can't be both of them that's gonna get oxidized. So which one of these are gonna get oxidized, and that will tell us which one we have to write the half equation for. So if we pick one.
OH.
Why OH?
It's because it's lower on the electrochemical series.
It's lower than sulfate on the electrochemical series?
Yes, miss.
And then what else? There's something else that can clue us in on it too.
Miss, it's dilute solution, miss.
Exactly. So okay. So the three things that we said when you're determining what get discharged is 1, the position in the electrochemical series, which you are exactly right. OH is lower than sulfate, so OH would be preferentially discharged from that standpoint. Then you have to think about the concentration of the species, so the ions. And because we're told that this is dilute sulfuric acid, we know that the sulfate ions are at a lower concentration when compared to the hydroxides that would come from the water, right? Because it's dilute. So because it's dilute, now we know that the concentration of hydroxide is also higher. And then thirdly, the third thing that you have to look at is whether or not your electrodes are inert or active. And because we have an inert electrode, we don't have to worry about that third criteria. But the first two criteria, the first one being the position in the electrochemical series, And then the second one, the concentration of the ions, both point us to hydroxide being the ion that's going to get preferentially discharged at the anode, right? So are we all good on that? So that's our second step. We complete our second step. Right? Is that clear to everyone?
Yes, miss.
So we can cross out this. We don't need this. Or cation. So at the cathode, we're going to write the half equation for the reduction of the hydrogen ion. And then at the anode, we're going to write the half equation for the oxidation of the hydroxide ion, right? So if I write in it now, at the cathode, so the cathode would be, so at the cathode now, it's hydrogen that's going to get reduced. So it would be H plus E to get me that H2. Well, yeah, to get me that H2 gas, right? That's reduction because we're going from +1 to 0. So that's our reduction. That's a change in our oxidation number, but this is not balance. So balance it, I have to put a 2 before the hydrogen, and then by extension, I have to put a 2 before the E because the charge has to be balanced as well, right? So that's at our cathode. And then now at our anode, where oxidation takes place, we're gonna be oxidizing the OH minus. And when we oxidize the OH minus, oxidation is lost. So this is gonna lose. So let me just put the E. It's gonna lose an electron to get water and oxygen gas, as I think Elizabeth pointed out earlier. So we're gonna get liquid water and oxygen gas, and we balance charge and balance everything. We're gonna end up with 4 OH minus. We're gonna end up with 4 electrons, and we're gonna end up with a 2 before the water. Can you guys see all of this? Is this clear to you? What's happening there?
Yes, miss.
Okay, so then now I'm gonna let somebody take it from there for me. So we're done, we're up to step 3 now, we're done. I just did 3 steps for you guys. Can somebody do step 4? Calculate the Q and tell me what Q is, and then we'll take it from there. Anybody wants to volunteer? In the interest of time, I need somebody to step up right now. No deliberating. I want somebody to just jump on and do that right now, because I want you guys to be involved in solving this. So what's our Q, guys? Q is equal to I times T. Our I is 2.5 amperes, and our time is 25 minutes and 44 seconds. And you have to convert that to seconds, all of that to seconds, because we're working in SI units, we can't use minutes. So we have to convert the 25 minutes and 44 seconds all into seconds. So what's that? So what's the time that we're using to find Q?
1,544 seconds.
What is it?
1,544 seconds.
Okay. So 1,000. Okay, so what's the Q? So tell me what Q is then. 1,544 seconds times the 2.5 ampere gives you what?
3,860 coulombs.
3,860 coulombs. Okay, that's great. So then now they're asking us to find what mass and volume of oxygen measured at STP will be formed at the anode. So right away, we don't really care what's happening at the cathode anymore. So let's look at the bottom equation then. So that's 4 OH minus plus the 4 OH minus 4 electrons goes to 2 H2O liquid and the oxygen gas. So we want to know what mass of oxygen we're gonna get from that. And you said that the charge is what? How much charge do we have?
Yes, 3,860 coulombs.
3,860 coulombs.
Yes, miss, that's right.
Okay, so then now what's the next step? What's the next step to find the mass?
No, sorry.
They say you can do the Faraday, you can find out how many Faradays that is. So how many Faradays is that? That charge that you just told me, how much is that in Faradays?
0.04.
0.04 Faradays, that's great. All right, but from our balanced half equation, what does that tell us about the amount of Faradays? So like theoretical Faradays, really, right? Let's work with the theoretical Faradays that we would need to form that oxygen. So let's do that. So we have, you mentioned that we have, how many Faradays? Tell me again, how many Faradays?
0.04.
So we have 0.04 Faradays, right?
Yes, miss.
From the anode equation, we say 4OH minus 4E gives us 2H2O plus O. Yes. So 1 Faraday is what we're concerned, is from a theoretical standpoint. That's what we're looking at here. And that's because the charge on the OH minus is, the size of the charge is 1, because it's OH minus, right? So from this, then we see that 1 Faraday, right? 1 Faraday is required to discharge 1 mole of OH minus 1 Faraday is required to discharge 1 mole of OH minus, but we have 4 moles that need to get discharged. So what would that be? How many Faradays would we need then, theoretically? Okay, let's think about it this way. We need 1 Faraday to discharge 1 mole of OH minus. If we discharge 1 mole of OH minus from the balance equation, guys, if we discharge 4 moles of OH minus, we're gonna get 1 mole of oxygen gas. Are we on the same page with that? If you discharge 4 moles of OH minus, you're gonna get 1 mole of O2 gas. That's what our balanced half equation tells us. Is that good? Are we good on that?
Yes.
And so in terms of Faraday's second law, we're gonna need 1 Faraday to discharge a mole of OH minus. But if we discharge a mole of OH minus as opposed to 4, how many moles of oxygen gas would we then get? We're gonna have to divide that by 4 too, right? So we would only get a 1/4 mole of oxygen from that. Does that make sense? 4 moles of OH minus gives us a mole of O2 gas. So if we're only discharging a mole of OH minus, that would give us 1/4 mole of O2. 1/4 mole of 0.25, right? That's what 1/4 is. 1/4 mole of O2 gas. So are we good on that? That's just doing ratios. The balance half equation tells us we need, if we discharge 4 moles of OH minus, we're gonna get a mole of O2 gas. If based on Faraday's second law, we know that 1 Faraday is what we're gonna need to discharge a mole of OH minus. And if we discharge a mole, only a mole of OH minus, we're gonna get a 1/4 mole of oxygen gas, right? So how much is all right. How much is a 1/4 mole of oxygen gas? How much is a mole of oxygen gas in terms of mass? Can somebody tell me that? How much is a mole of oxygen gas in terms of mass? What's the molar mass of oxygen gas?
32, miss.
32, right? So a mole is 32. So quarter mole is what?
Eight, miss.
8.
Is 8, right? So quarter mole is 8. So one Faraday, guys, is gonna get us 8 grams of oxygen. So now back to the question at hand. That's what 1 Faraday would get us, but we don't have 1 Faraday. Based on your calculations, we have 0.04 Faraday, right? Right, guys? Based on your calculation that you did for that Q and then the subsequent Faraday, you told me that all we have is 0.04 Faraday, right? That's all we
miss.
have. The 1 Faraday is a theoretical amount, but in real life, we only have 0.4 Faraday. So what mass of oxygen is 0.4 Faraday gonna get us? What mass of oxygen is 0.4 Faraday gonna get us? 1 Faraday got us 8 grams. So if we only have 0.04 Faraday, what mass is that gonna get us? So what is X? X grams of oxygen. What's X in this case? X is 0.04 times 8, which is
0.32.
0.32? 0.32 grams of oxygen. So that's our answer. That's the mass. That's the mass that we're gonna get, right? So we got the first part of this question down. Are we all good up to that point?
Yes, miss. Good so far.
Okay, so we have our mass. So I'm gonna let one of you guys do the leap to volume now, because this is just like mole concept now, you know. We got the mass, check. That's 0.32 grams of oxygen. So I'm gonna show you a trick to make the last part easy. Let's go back to the amount of moles. Okay, let's convert the 0.32 grams of oxygen to moles. What mole, convert that to mole and tell me how much that is. What is 0.32 grams of oxygen in moles? What's 0.32 grams of oxygen in moles? We know that 1 mole of oxygen is 32 grams, right? So 0.32 grams would be how many moles? .32 grams of oxygen is how many moles? Anybody? It's not a trick question. It's not a trick.
I said 0.01.
Okay, so it's 0.01, right? So let me see, we have something. 0.01 moles of O2 is what we have essentially, right? We just converted this to mass, to moles, right? Oh no, why did I? Oh no. So 0.01 moles of O2 is what we have, right? But we know that at STP, 1 mole of gas occupies how many dm cube? At STP, 1 mole of gas occupies how many dm cube?
Measurement.
22.4.
22.4, that's exactly right. That's how much 1 mole would occupy. But we don't have 1 mole. We have 0.01 mole. So how much volume is that 0.01 mole of oxygen then gonna occupy at STP? And that's your final answer. Anybody wants to calculate that for me and let me know? 1 mole occupies 24 dm cube at STP, but we don't have 1 mole. We have 0.01 moles of O2, and that is going to occupy what volume at STP?
Miss 0.224 dm cube.
That's exactly right. That's exactly right. All right. So I think that we're gonna stop here for today. But I think what I attempted to do is really give you, like, lay the foundation for how to approach these questions, because I think we did a good mix of them. We did single charge species, we did some doubly charged species, we did species where you have competing ions and you have to decide what's gonna get preferentially discharged. I think we did a very good blend of questions today. So I hope that this was helpful in terms of like laying the groundwork or a methodology for how to approach these questions. And so what I could do, given that we're gonna be off for some time because we start the past paper marathons on the 17th, I believe, the 17th of April.
Yes.
Yes, the 17th of April. So we're not gonna be meeting. You and I are not gonna be meeting for a while. So I'm gonna. What was that?
Unfortunately.
But we can still interact, right? We can interact on Instagram, and I'm gonna send you quizzes to do in between to like sharpen your understanding of these things. And I'll start with an electrochemistry quiz I'm gonna send to you guys, and just work through that, and then we'll reconvene for the past paper marathons. But like in between now and then, I'll like send you guys a bunch of quizzes that you can do on your own time, right? And then now when we reconvene with the past papers, and hopefully by you practicing and like rewatching these videos, going through and rewatching it, everything will just be like crystal clear. So once you come to the past paper marathons, you're like, oh yeah, obviously, like that's what I hope. That's where you'll be at the past paper marathon sessions. If not, that's fine. But if you are there, that would be great. And then by the time the exam comes around and you see the question, of course, I don't want you to be like overconfident and make mistakes, but I want there to be a certain level of confidence, given that we've done so much practice. We've also done fundamentals, understanding the concepts. I want you to be at a comfort level by the time the exam comes around that you're just like so comfortable. When you see an electrolysis question, a mole concept question, or anything, you'll be able to do it, right? But because I focused largely on mole concept and electrochemistry for these free sessions, it is my hope that you'll have an exceptional grasp of those topics, those 2 topics. That's my hope. But we'll see.
Yes.
Okay, guys, so that's all for today. How we do? We did an hour and a half. That's pretty solid. I'm pleased with that. What do you guys think? How are you feeling now?
It was good.
Yeah? Was it,
yes.
Did you learn a lot? Did it clarify things for you and so on and so forth?
Yes, miss. I got a lot of clarification, and I was able to actually follow the steps and doing them while they were working through everything.
Okay.
So yeah, everything cement.
That's good. That's what I like to hear, right? So that's very good. So that's Elizabeth. How about Claudia Barry? How about the rest of you guys? Let me hear from all of you guys, because I'm not going to speak to you guys for the next few weeks. So let me know where you are today, right? And of course, I'm going to send practice questions for you to like really sink it in. But where are you today? Jabari, where are you with this? I know that we had discussed this question in particular before. Where are you on this today, Jabari?
Yes, well, I did join the class late, but I'm catching on. However, for the part where 4 moles in the first when I was finding the mass miss, got thrown off a little bit right there.
Okay. Okay.
But other than that, miss, I'm overall good on this subject now, a lot better than before.
Well, you see, you're so soft-spoken. I can hear what you're saying, but I have to be like this.
Yes, miss, I'm not sure what happened to my device.
Okay, but you said that overall.
It's great, it's great.
Okay, that's good. Okay, Kayla said, I haven't learned this topic as yet, but I understand it very well, miss. I'm very happy to hear that. That makes me so happy. So yeah, that's great. I'm gonna send you a quiz as I mentioned for you to keep working at this. And then in your own time, look up the examples, look up the applications of electrolysis, because it's very cool. It's actually a very cool something that you can apply, and it applies for like coating cars and stuff like that. Like there's something called anodizing. There's a bunch of applications, right, that you can apply, you can use electrolysis for. And that's why I love chemistry, you know, guys. It's like everywhere around us. It's just so fascinating. So in your own time, look up the applications, look up the examples so that you're comfortable with that. Because oftentimes the question that you're going to get is an applied question. They want you to apply your knowledge. So look up the applications, look up the examples, and with the foundation that we've laid through these classes, you should be able to connect the dots for yourself, which is the goal ultimately of learning, is that you can apply your knowledge. It's not a swatting thing. You understand it at a fundamental level so that you can apply it. That's my hope. And so do that for me and look through the examples, look through the applications, and then let me know what you think of electrolysis and electrochemistry as a whole, right? So we're gonna end here for today. But whenever I'm taking it that you're all subscribed to the YouTube channel, you can go back to the YouTube channel and rewatch this. Make sure that it like sinks in. While you're watching the YouTube channel, of course, subscribe to the YouTube channel, but make sure that you like it. Like the video, give it a like, give me a thumbs up so I can see that it's like, it's good. You can even drop a comment and say, hey, miss, blah, blah, blah. Or if in rewatching it, you realize that don't make no sense. Miss, that don't make no sense. Ask me underneath the video. Interact with the video is what I'm saying. Okay, guys?
Yes, miss.
All right, then.
Miss, you said that you were going to give us the account number.
Yes, I'm gonna send it to you. So Elizabeth,
Miss,
send
I
me.
remember my message.
Oh yes, Kelly, I'm gonna reply to your message too. Send me, Elizabeth, send me your email address.
Okay, I'm going to do that now.
Okay, send me your email address and I'll send you the bank information and so on. And Elizabeth, you're at Distinction College, you said, right?
Yes, miss.
Tell all your classmates them, okay?
Yes, miss, I've told a few.
Yeah, tell them all about it. Tell them say pass paper marathon a giveaway for cheap and free. So tell them.
Definitely will.
Tell them to come. And of course, that applies to all of you guys who are here too. Tell all of your classmates. If you have friends in sixth form, tell them about the sixth form one too, right? That they should come and really crystallize their chemistry concepts and get their past papers, get it all in, okay? So that's where we are. But thank you guys. Thank you for being here for the entire duration of this LMD and Chemistry Sundays, this free chemistry series. But unfortunately, we're done with the freebies for now. Well, there'll be freebies on the Instagram. Like I'll have content on the Instagram for free. And I will maybe I'll upload some content on the YouTube channel. But in terms of like class where it's like this and it's like all free and da-da-da. Unfortunately, we are done with that for now. And we're moving on to paid past paper marathons. Okay, guys? But thank you so much for being so consistent and showing up every week, showing up for yourselves to learn and really understand chemistry at a fundamental level. So you're supposed to be commendable. Is it commendable So thank you for that. And yeah, give yourselves a clap.
Yes,
And,
and to you also, Miss.
yeah, you're most welcome. So yeah, so goodbye guys. Have a great rest of your week, and I will see you on April 17th, and I'll send out like account information and so on for payments for the Passover marathons. Okay. All right.
Thank you.
All right, bye.
Bye.
Thank you.
Bye.
Bye.
Bye.